Homework solution 4.8. A synchronous generator operating alone is configured to have a no-load frequency of 62 Hz and has a slope of 1.5 megawatts per hertz. Determine the frequency of the generator when connected to a load of 1.2 megawatt at 0.85 power factor lagging. A second load is added to the first. Load 2 consumes 1.14 MVA at 0.707 power factor lagging. What's the new operating frequency of the system? And to what value should the system operator set the governor no load set points to restore the system operating frequency back to that found in part A? The givens here are that we have a no load frequency of 62 Hertz. The frequency droop characteristic is 1.5 megawatt per hertz. So that's all we're given. And then we're asked to find FSys at 1.2 megawatts, power factor equals 0.85. FSys at 1.2 megawatts, power factor 0.85 plus 1.14 MVA, power factor equals 0.707. And then in part C, we want to restore the system back to the frequency here, and we do that by adjusting F and L. So what's the new no load frequency? So those are what we're asked to solve for. The solution for this problem is based on the concept of a droop characteristic. Droop characteristics are that as we increase power, the frequency of a generator is going to typically decrease in a linear fashion. So we plot electrical frequency on the y-axis and real power on the x-axis. And the change in frequency as a function of increased power just looks like a straight line that's decreasing as power increases. The point where that straight line crosses the y-axis or the 0 watt axis is called the no load frequency, or sometimes the generator set point. And then what we do is we find the power, the load power demanded by the generator, just draw a line straight up until it intersects with the droop characteristic plot, and then go straight back and find out what that XY coordinate is right there. And that's the system frequency FSys. The slope of this line is that SP, which is 1.5 megawatts per hertz. And F no load here was 62 hertz. So a lot of times I say that the slope of this line is 1.5 megawatts per hertz. Clearly the slope of this line would need to be in hertz per megawatts, but that's just for mathematical reasons it's given as an inverse slope. The formula that governs this plot is that the power sourced by the generator is equal to the frequency droop characteristic times the generator set point minus the system frequency. P equals SP times FNL minus FSys. So that's the information we need to have to start solving the problem. In part A, we were told that the load was 1.2 megawatts at a power factor of 0.85. Well, if we look at the slope characteristics or the frequency droop characteristics, all we need is power. So the power factor in this part of the information is extraneous. We don't even need that. So that's just 1.2 megawatts. So we've got that. We need to set that equal to the slope, which was 1.5 megawatts per hertz. The no load frequency was set to 62 hertz, or the generator set point. So now we can determine the system frequency just by solving this equation. Clearly all we need to do is divide both sides by 1.5 and then subtract 62 from that, and we find out that this generator system is operating at 61.2 hertz. So little bit high. Anyway, that's what it's operating at. What happens if some more load comes on? Well, we know that just qualitatively, if we add load because of the slope characteristic, P will increase. That means F_sys has to decrease, but exactly how much? To solve that, we just take B. The load's going to increase into 1.2 megawatts plus 1.14 times 0.707. Right, so the load information for load 2 was given in apparent power and a power factor, so I have to convert that over to real power, which I've done right there. And that's going to be equal to 1.5 megawatts per hertz times 62 minus F_sys, right? It's the same calculation, it's just that the total load power has changed. So the system frequency is going to decrease to 60.66 hertz. The addition of that load caused the frequency to go from 61.2 to 60.66. So in part C, we're asked, okay, well maybe we wanted the frequency to be at 61.2 hertz for some reason. What do we have to do to change it? Well, the thing that we can change in this diagram is we can move this line up and down. We could have a different line right here. Can't change the slope, that's fixed, but we can move where it intersects by just increasing the torque provided by the prime mover. And so what we could say is we've got these two powers together, which if you add those together, it's 2.00598 megawatts. That's going to be equal to 1.5 megawatts per hertz. And I need to change the no load set point of the generator, so that becomes the variable that I'm going to solve for, and I wanted to go back to 61.2 hertz. So now all I have to do is solve this equation, and I find F no load is equal to 62.5373 hertz. So before I was at 62, so I need to increase the no load frequency by 0.5373 hertz. That'll restore the system frequency back to 61.2 hertz for this larger load that we have calculated in part B and C.